Hey everyone, and welcome to our tech session for this week. We are going to be discussing ecosystem on Kubernetes. So just to give a bit of a highlight quickly, Kubernetes is an open source system for automating the deployment, scaling, and management of containerized applications. And it's Eric that's going to be taking us through the process today. Yeah, if anybody's got any questions, feel free to ask. Eric, feel free to take it off.
Thank you. So I'll be talking through how to deploy ecosystem on Kubernetes and some things to think about while you're doing so. I'm going to be just illustrating the deployment on MiniKube, but this, principles and the approach will apply across whatever Kubernetes style infrastructure you're looking to deploy on. So what I'm going to be talking through the deployment of 5 of the ecosystem components: the server, the Workbench, the notebooks, Grafana, and the runtime. First thing that we're going to create in Kubernetes is the creation of a secret that contains your license key for the product. You'll create that in your namespace, and we'll use it as an environment variable for starting up the various containers. Before you do that, you probably want to create a namespace for your deployment. In this case, we'll be working in the ecosystem namespace. In that namespace, create a secret with your key. You then create a config map that has the environment variables that we want to set for our deployment. We've got variables for the server, the port we're starting up on, the route for the service that will be created, where you want your properties to be stored, and the fact that we are having a separate workbench and spinning up Mongo inside the server. For the runtime, we set the port we wanted to start up on and the monitoring delay. This is one of the fields for your dynamic recommender setup. For the workbench, you need to set the IP where the workbench can use to communicate to the server. In this case, it will be my local host because I'm doing this on MiniKube, but this would be the ingress that gets created in Kubernetes to the server. Depending on the Kubernetes provider, that could look different. Finally, for Grafana, we allow embedding so that we can view some of the Grafana dashboards in the workbench, and we install a couple of plugins as part of the deployment. So we go ahead and create that config map. So all of our deployments we're going to be doing using kubectl, not doing Helm charts, YAML config files for the different components we're deploying, and we'll just be applying them using kubectl. So we've now got our config map. The next thing you're going to want to create is your persistent volume claim. This is where you have your first decision point, depending on what your Kubernetes environment looks like. Ideally, you want to create a single ecosystem data persistent volume claim that is going to persist all of the configs and logs generated by the various ecosystem deployments. To do that, you need to create a read-write many persistent volume claim with sufficient storage. Many Kubernetes infrastructures don't support the creation of read-write many persistent volume claims. So if you can create a read-write many, then it's relatively simple. You just create one and that gets mounted to everything. If you can't, then there's 2 approaches that you can take. So then you need to create read-write once persistent volume claims, and those can still be mounted to multiple deployments, but the deployments need to be on the same node in your Kubernetes infrastructure. And the key components that we want to to share a persistent volume claim are the server and the runtimes, because that allows for easier management of the runtimes from the server. For example, things like viewing the runtime logs for the different runtimes you have deployed from the server is only possible if the server and the runtimes are sharing a persistent volume claim. If you have write many, then that's easy. If you have read write once, in order to have that happen, you need to set the pod affinity for the runtimes to be on the same node as the server. The downside of that is, one, you're going to have a lot of load from the ecosystem environment on one of your Kubernetes nodes, but it also concentrates your risk. If one node goes down, all of your runtimes and server are also going to go down, which is generally not something you want to have happen. My recommendation would be, if you have to have read write once, that you forego the easier management of the runtime via the workbench and the server. But if you can accept the concentration risk of having a lot of things running on one Kubernetes node, you can use pod affinity to ensure that the runtime pods start up on the same node as the server pod, and they'll then be able to share that read write once persistent volume claim. The other thing to note here, and that might be different in different deployments, is assuming that either Mongo is running in the server or that there's a separate Mongo instance being created and used. If you are running Mongo in Kubernetes as part of the ecosystem deployment, then you would want to have separate persistent volume claims for the Mongo data. Mongo has requirements and strong recommendations around the formatting of those, so they need to be a specific file system and all those sorts of things. Separate persistent volume claims for Mongo as well. But let's assume that we can have a single persistent volume claim. The only difference would be, if we're not doing it like this, that you have to refer to, maybe you create an ecosystem data runtime 1 PVC, runtime 2 PVC, and you reference those, but everything else will be pretty much the same. So we can again use kubectl to create our persistent volume claim. If we go to our dashboard, we can see we've got our ecosystem environment config map, and we have our ecosystem data persistent volume claim. The next thing we're going to spin up, or the first real component we're going to spin up, is the server. So for that, we have a deployment YAML. We create a single replica. Generally, the server is not something that you would need to scale horizontally, and that will apply to most of these. It's really the runtime that needs to have horizontal scaling, and we'll talk a bit more about that when we get to it. We've got our server. Basically, the way we set up the pods or the container is we point to, in this case, this image on Docker Hub. Generally, best practice would be to have some sort of local image repository that you can pull from, just so you don't end up hitting Docker Hub rate limits and things like that. For this kind of local version on MiniKube, using Docker Hub is fine. And we get the server image, and you can either get, depending on your architecture, you can set the right tag. We are setting the image pull policy to always, because we always want the latest version, but if you can set it to if not present or never, if you want to be more deliberate about incrementing versions. We set our environment variables. The first one is our master key, which we set from the secret that we created that has the ecosystem license key in it. Just by getting the value from the secret key ref, I called my secret master key, and the name of the value in it is also master key. Then we reference all of the environment variables that were part of our config map that we created. We have the server port, the IP, the location of the property file, the CLI settings, the user, and the fact that we're not spinning up the workbench as part of the server. Then we expose the ports that we want to be exposed from these pods. So the first one is 3001. This will be the main port that you use to interact with the server. As part of the server spin up in this demonstration instance, we're also having the server spin up H2O and Mongo. So Mongo and H2O are both being run in the server pod. So we then expose the ports for those two components. H2O is on 54321 and Mongo is on 5445. So this will then enable those components to be interacted with, as well as interaction with the server itself using the 3001 port. And then we mount our ecosystem data PVC volume, and we're going to mount /data, which is going to be the path that's shared across our different deployments. So we mount that in the data subpath in our PVC, and then config where they're stored in the server config subpath. Spin up an instance of the server in your Kubernetes environment that will be running Mongo in addition to the server. We then need to create services in order to allow interaction with these components on these ports. So we're going to create 3 services, one for the server itself, one for Mongo. So I'm not actually using H2O in this demonstration, so I didn't create the service, but you would then create an H2O service on 54321 to interact with that. You'll see here, these are load balancer type services. That's because for this version of Kubernetes, that's how the ingress can work, is by creating a load balancer service that allows traffic from outside of the Kubernetes cluster. You can also create a cluster IP service if you have a different form of ingress that you want to create. The cluster IP service will then allow interactions within your Kubernetes environment. You do need to create a service for each port. You can't just create a single service that references all the different ports. So for each component that you want to expose, you'll need to create a service. So if we apply our server deployment YAML, so these are unchanged for the sake of expedience. He set these up beforehand so we wouldn't have to wait for the container pulls and other image pulls to happen. But you'll see we now have our ecosystem server deployment and a corresponding ecosystem server pod. We can look at the logs of that pod, and also if we want to go into the pod itself, you can go into it and see what's in the mounted data volume. We've got our interaction science module that we loaded up and the logs, so we can go and see the different logs. And this is why it's nice to mount things to the same volume, because now I can see, if I want to see what's happening in that runtime. I mean, there's obviously more graphically friendly ways to do this, but you can also do it in the command line. You can go in and view the logs of the runtime server in Mongo. So we've now got our server started up successfully, and we have our services created for the server and Mongo. And you can see, because we created a load balancer service, there is an external endpoint created for that service, and we can access it. So we can then access the Swagger for the server and engage with it in whatever way we want to. So that's setting up the server, which is kind of the core of your deployment. You can then create the Workbench and the runtime. So we'll first talk about the Workbench. Some of you might have noticed when I was showing the config map before, there was an extra config map server you can create for the Workbench. By default, it starts up using port 80, which requires elevated privileges in some environments. You can use this Nginx config to change the port that the Workbench starts up at. So here I'm starting the Workbench up on 8008. So that's the purpose of creating this config, and it'll then mount this config to our Workbench deployment. For that change to take effect, we are pulling the image from Docker Hub, but best practice would be to use some sort of local repository. And you can see that we are mounting our config map in order to pull in this nginx config. So we're mounting it to etc nginx-conf.d, which is just the default nginx path for this. We are also running as group 0. This is to allow the startup to have access to the required config files when it's starting up. We don't want to run as user 0 and have root privileges. So we can use run as group in order to give the required file permissions without requiring root access. And then we've got our environment variables that we spoke about before in the config map with our IP and the port that the Workbench is going to use to communicate with the server. And then finally, we have our port that we're exposing, which is our 8008. We're going to create a service to expose the Workbench port. So again, we create a load balancer service on 8008 to talk to the Workbench. So if we go back to our setup, you can see in our dashboard, we've got a Workbench service, Workbench deployment and pod that are running successfully. We see we have an external IP, and now we can log into the Workbench and use that to more easily do some of the things I was showing before to interact with the server. So, if we wanted to see the runtime logs, because we have that shared persistent volume claim, we can do that here and do everything else that we normally do in the server and the Workbench. I'm not going to go into too much detail on that because it's been covered in lots of other sessions, and I'm sure will be covered again in future. Then we create our Workbench, our runtime deployment. So there's a few decisions to make here. We're not doing the pod affinity thing here because we have our read-write mini. If you decide to go the affinity route, you can use this approach to make sure that the runtime starts up on the same node as the server. Also requires you to make sure that the server is started up before you start the runtime. The other thing that you need to decide is how you want the scaling of the runtime to happen. So the one option is that you can have a fixed number of replicas. This would be if you are confident in your traffic volumes and want to have kind of full availability at all times, and say, that for this case that you're deploying here, kind of five runtimes, say, would be sufficient to deal with the traffic, even in the most extreme cases, or if you're going to manually adjust it when a big event in your environment, like Black Friday is coming up, you can manually scale it up. In this case, I'm just going to show how you can do it with an autoscaler. If you're doing that, it's recommended that you don't manually specify the number of replicas. So you would leave your replica number out of your config and use an autoscaler to manage it. We're going to mount our data, have our environment variables set up, putting our image, exposing the port. The one thing that you'll see is different here is we are explicitly specifying the resource requests and limits for this deployment. And we're also setting the requests to be equal to the limits. Obviously, you don't have to do it like this. You can set it up however best suits your environment. But I think from our experience, having a guaranteed quality of service for the runtime, given that it's generally a production critical deployment, is quite important. So our recommendation would be to set the resources to be the same as the limits and have that guaranteed quality of service. That's why we specify those here and why we've decided to set them to be the same. We exposed the runtime port as a load balancer service, which we can take a look at from our dashboard. We have our our runtime deployment, our working runtime pod. I guess I should just run the command so it's now gonna set this up because I was playing around with it before. That was a bit odd. Let me just get rid of that. Doesn't need to be there.
Eric, it won't be Kubernetes unless there's a configuration that has to be adjusted.
So now our runtime is spun up and it's running, and we have our service exposing that port so we can access the runtime from outside of the Kubernetes environment. Just to show the one thing that you need to change then when you're working with this from the kind of default Docker or Podman cases, so I've imported the interaction science module into the server. If you go to projects, you can see we've got the interaction science module loaded. And if we go to the deployments, the main thing that you need to be aware of when doing things in Kubernetes is that the connection details between the components are different to how they look in the standard Docker case. So there's two ways that you can do it. You can either get the cluster IPs, which is what I've done here. So you can see we want to point to runtime 1. So we've got this cluster IP, which is the same there. Or you can go and do a namespace lookup for the path that the service can be referenced with internally. So that's generally something like runtime.ecosystem.svc.cluster.local. In a way, it would be similar to this, just with .ecosystem.s, but you do need to change these connections from the default Docker version to something that makes sense in your Kubernetes environment. So here we've got the Mongo IP that we've changed as well. Once we've made those changes, we can do a push from the Workbench for our deployment. And then that's been successful. If we go to our laboratory, we can do our test API call. You have to change your API path to reference the right place in Kubernetes. Then you can make a call and get a result back. So that's kind of the Workbench server runtime. The last piece for the runtime is the scaling. So setting that up in Kubernetes is relatively straightforward if you just use kubectl. So we just create an auto scale on the deployment ecosystem runtime 1. And for this case, I just said we want 1 to 3 replicas. So this you would set depending on your environment and resources and anticipated load. And then we're saying scaling by the CPU utilization. And when that goes above 70%, we want to spin up additional pods in order to use horizontal scaling to handle that load. You would create your auto scaler, but yeah, that's what you can do to set that up. Generally, you would have multiple of these runtime deployments for the different cases that you have, and have an auto scaler created for each of those runtimes. The last piece is our ecosystem notebooks and the Grafana deployments. We, again, get the image from Docker Hub. Here we expose 2 ports. So the notebooks container fulfills 2 pieces of functionality. The first is it provides a Jupyter Notebooks environment that you can use to interact with everything else in the ecosystem Kubernetes setup that you've created. It has a few Python packages pre-installed to make that easier. There is the Python server, which is a kind of a server that does various pieces of work, particularly in the kind of generative functionality space. We need to expose both of those ports. We then map our shared persistent volume claim. If you can't do that, you would have to have created an ecosystem notebooks PVC. And we create a couple of directories used by the environments. to store the notebooks that get created. And if we have a shared persistent volume claim, we can also mount the data folder just for easy access to files across those environments. It's not required that this is there. You can interact with the data in a range of different ways. This is all that you really need to persist your notebooks for your setup. This is a convenience factor if your environment supports that read-write many persistent volume claim. And we have our 2 services that we need to create in order to expose those 2 environments. And then finally, we have our Grafana setup. There's a couple of ways you can do this as well. Here, just illustrated one of them that we've created, where depending on the internet access your Kubernetes environment has, you might not be able to have some of the automatic pre-configuration and plugin installation happening. We have a no JWT version of the container that can be used in that case. But if you can do that, if you want some of the stuff to happen automatically, you can use the latest or 64 versions. And again, we mount Grafana to persist some of the information. We expose port 3000 there and create that service. If we run that last bit of our setup, then we'll have our deployments that are created and the pods linked to them and the services that can be used to interact with them. For example, if we go to our Python server, do we try the notebooks one? Yeah. So we can go to our notebooks and go through the process of creating a user. And log in with that user. And start up our server. Hopefully. And then we have a couple of kind of pre-configured structures and notebooks that you can use as a starting point, or you can create your own and work through those. I'm not going to go through using the notebooks to interact with the server. I think that's another session that we can go through. So yeah, that's how you do a basic ecosystem install. The 2 pieces that I haven't included this week are Superset and Airflow. Those are more involved to set up. We use their Helm chart setups with some custom values and a couple of other things you need to set up. We can maybe cover those in another session, but this will give you a pretty close to complete setup of the ecosystem components in Kubernetes with automated horizontal scaling on your runtime and everything linked nicely together and talking to each other. As you can see, when it's idle, it doesn't actually require that much resourcing, but obviously that scales up as your usage increases and you have more people engaging with the setup components and more predictions being run through the runtime. So yeah, that's what I was aiming to cover today. I don't know if there's any questions.
No, I think that's great. Thank you very much, Eric.